if you look at your notes, and we're not going to talk for super long about these, I'm going to give you some equations, we're going to do a couple problems, and you're going to have a little bit of time to work. We have really exponential growth and decay is actually one function. The difference is that there is one time a plus sign and one time a minus sign. It's kind of like quadratic formula where you have a plus and a minus, but it's the same thing both times. Exponential growth is saying that y equals a times 1 plus r to the t power. That is our exponential growth equation. So, and the important thing with exponential, and the thing that I emphasized when I'm teaching this in Algebra 1, is exponential functions have an exponent of x. That's their variable. The thing you don't know is your exponent in this case. So everything we're dealing with and what we've been dealing with for the past couple days, because we even did transformations already. We did transformations of exponential functions. So exponential growth functions are going to be increasing. They look like this. That's important. Sorry, they look like this. And one of the things y'all learned was they have a horizontal asymptote. So, and that horizontal asymptote is based on like how much it moves around. Which our graphs, the horizontal asymptote, what do you think it's going to be for exponential growth and decay problems? Yeah, it's 0. Because whatever we're talking about can never get to 0. Like if we have like a value of a car, for example, is the value of the car ever 0? No, it can get really, really small, but it's never actually ever going to be 0. It's just going to keep, like, maybe you taking half every time. Well, it's just going to continue to get closer and closer to 0, but it's never going to be 0. So that's exponential growth. And then our exponential decay equation, well, that's super easy because it's the same formula, but instead of plus in the middle, it's minus. And an exponential decay problem, or graph, is going to look like this. Again, with the horizontal asymptote of 0. Meaning it's just going to get closer and closer and closer to 0, but again, never actually be 0. So those are our two formulas, which is really just one formula with different signs in the middle. That's it. Based on what you know about geometric sequences, what do you think A represents there? What you start at. It's your initial value. It's exactly right. So just like with the geometric sequence, that first number was our first term. This is our initial value, whatever we're starting with, the initial amount. So you have some common sense there. So what do you think that T represents? Time. Yes. T is your time. Okay, what about R? Any guesses what that is? Close. It's actually not your common ratio in this case. It's something different. It is your growth or decay rate. R is your growth or decay rate. R is your growth or decay rate. And we need to just include in here that we need to convert it to a decimal, because usually it's going to be given to us in a percent. Convert to a decimal. Out of curiosity, does anybody have trouble remembering how to convert from a percent to a decimal or vice versa? And it's okay if you do. Nobody? We're all good with that? Well, for anybody listening out there in the world, in case you do, well, the way I remember how to convert between the two is I remember Dr. Pepper. That if you're converting from a decimal to a percent, you move it 2 places to the right. If you're converting from a percent to a decimal, you move it 2 places to the left. This 1 plus or minus R, this is what is called the growth or decay factor. This is what is called the growth or decay factor. And what this is, really, this is how much is left, or how much you have, sorry, I'll say that, how much you have after each iteration. It is how much you have after each iteration. Iteration is like each time you do the problem. So, for example, like if you started off with $100 and each month I took away 5. So you're starting off with 100, you're losing what percentage, or sorry, I took away 5%, not $5, I took away 5%. So after the first month, how much money do you have left? $95, which really means you have 95% of what you started with, correct? And each month thereafter, you're going to have 95% of what you had the month before because you're losing that 5%. That's what your growth factor is. Okay, so the percent is how much you're losing or gaining, and the growth factor is like just the amount that'd be left over after that. Sometimes it's more than 100. You may be gaining stuff. We'll talk about that kind of in each problem that we look at. So this really isn't complicated. It's just about us writing formulas and getting information, which that y'all are good at those things. Y'all like those things. So the value of a truck purchased new for $28,000. What information did they just give us? The initial value, the starting value. So we know that A is 28,000. It's a terrible looking A. A equals 28,000. Decreases by 9.5% each year. So what information did we just get there?
The R.
R, we got the growth or decay rate. Is it growing or decaying?
Decay.
How do you know?
It decreases.
Yes. So my decay rate would be 9.5%. And if I want to convert 9.5% to a decimal, that would be what as a decimal? 0.095. Yes. Okay, well now I have enough information to write my equation. We'll get to the rest of this in a second. So my equation will be y equals 28,000 times 1 minus 0.095 to the t power. T is just our time. Now that I have my equation, I can actually answer questions. Well, can I fix that and make it look a little bit better? What could you do? Yeah, you could simplify the parentheses. What is 1 minus 0.095?
Oh, it's a 1?
Yes.
That was an L. 1.8. 1 or 1.5.
Okay, it'd be 0.905. 0.905. So just to refer back to what we were talking about a second ago with our growth and decay factor. And you don't have to write this. I'm just talking about it because you need to understand this. 0.905 would be your growth factor or decay factor. In this case, would it be growth or decay? Which one? Decay. Convert 0.905 back to a percent. So what this is saying is after each year, you have 90.5% of what you had the year before. That's basically like your common ratio. What you're multiplying by every time is 0.905. Okay? That's essentially what that is. So if I keep reading, now it says we wrote an exponential function, did that. Use the graph to predict after how many years the value of the truck will be $5,000. So my value of my truck is decreasing. It's decreasing at a pretty steady rate. So we need to figure out when it's going to be $5,000. So we're going to graph it. Okay, so our equation was y equals 28,000 times 0.905 to the x power. And your calculators, either whether you're using Desmos or this one, you're just using x for your variable because it doesn't recognize t as a variable. And we're just trying to figure out where it hits 500,000. Or sorry, 5,000, not 500,000. Oh, there it is. There's 5,000. Did you know, by the way, that you can graph y equals 5,000 in the second one? And this works in either calculator. And then it will graph both of them, and all you're looking at is where they intersect. Where do they intersect at?
17 years and like 3 months.
Yeah, 17 years and some months. That would... So roughly after... so when will it be when will it be worth $5,000? So roughly a little bit after 17 years, or between 17 and 18 years. So I'm going to write that. I'm going to write between 17 and 18. That was a terrible looking between. There we go. Between 17 and 18 years. Okay, we're going to skip the next question and go on to the next question. I'll come back to the one about Tony purchasing a rare guitar. but we need to look at the third question on here. The value of a sports car purchased new for $45,000 decreases by 15% each year. Write an exponential function for the depreciation of the sports car and plot it along with the previous one. So we're going to compare this one to the first one that we did. Okay, what's my initial value in this problem? And it's decreasing by 15% each year, so that's my decay rate. How would I write that as a decimal? 0.15 or 0.15. And then I can write my equation. So 45,000 times, what would end up in my parentheses when I wrote this equation? 1 minus 0.15, which would be what? 0.85. So my decay factor of this problem would be 0.85. That means every time I have 85% of what I had before. So there's my equation. Then it wants to know, after how many years will the two vehicles have the same value if they're purchased at the same time? So what am I looking for at that point?
Solution.
How do I find that? What am I looking for on the graph?
The spot where you intersect.
I'm looking for the intersection. I'm looking for where our two graphs meet, where our two graphs intersect each other. So same graph we previously had. 28,000 times 0.905 to the x power. And I'm graphing my new one. Was it 45,000? Yes. Times, nope, 0.85. Oops, didn't like my decimal. 0.85 to the x power. And again, I'm going to have to zoom. One of the things on Desmos, I don't know if y'all know this, but if you... Okay, so I found the intersection. So when are they the same? Somewhere between 7 and 8 years, closer to 8 years, like maybe 7 years and probably like 7 months or something like that. So somewhere between year 7 and 8. So I'm going to say 7 years and 7 months. And that's a rough estimate there. So around 7 years, 7 months is when they were the same. Tony purchased a rare guitar in the year 2000 for $12,000. Experts estimate that its value will increase by 14% each year. Use the graph to find the number of years it will take for the value of the guitar to be 60,000. So I can write my equation. What would it be? Y equals 12,000 times 1.14 or 1 plus 0.14 because it was increasing at 14%, so it'd be 1.14 T. And then we want to know when it's going to be $60,000. So again, the same thing, we can graph it. You can use your table to find this information out too. Okay, but the table is just a little bit harder to estimate because it doesn't show you the values like in between. It only shows you what it asks for, like only typically shows whole numbers. Do y'all know how to adjust the table to show you what you needed to show you if you wanted a better breakdown? So if you need your table to give you something different, like in this case, so we had, what was our problem? I can't see. 12,000 times. Okay. So when you go to your table, the way it's set up is it automatically produces whole numbers. So if you go to your table settings are right here above window and they're blue. So we're going to hit second table set. This is where you can control a lot of stuff with your table. First of all, you can control where it starts. Like if you need to go to 10,000 because that's where you need your table to start at, you could type in 10,000 here. And then when you go to your table, that's the first number that's going to be there is 10,000. Okay, so you don't have to scroll all the way to 10,000. If you need to go back to 0, you can just hit 0. This right here, this symbol, this is a symbol y'all have seen in physics, right?
No.
Yes, delta. What does that mean? The change in. So this is saying the change in your table, it's currently changing by ones. So if you wanted it to change by 0.1, you could change that. And then when you go back to your table, then it will just give you like intervals of 0.1 instead of whole numbers. Did you type in 0.1 there for your delta table?
Oh, because I didn't change the top part of my
Okay. And then probably my favorite tool that I love about the table is this option for independent auto versus ask. Oops, sorry. And I love this one because when you change it to ask, your table is now completely blank and you can type in the specific values you want. So if you wanted to see 15, 25, and 35, you could type in those numbers and it would produce those values for you instead of you having to scroll around to find them. So when does it get to be $60,000?
It said error.
It said error?
12 years.
12 and a half.
Yeah, 12 and a half. So remember, when you're looking for $60,000, you're not looking for your X to be 60,000, you're looking for your Y to be 60,000. So it was somewhere around between 12 and 13 years. So I'm just going to write that between 12 and 13 years. And then if you look at the back, I'm going to do the middle problem off the back with you. And then I'm going to give you the work and y'all have time to work in class today. Okay, middle problem in the back. The population of bacteria in a water sample is represented by the equation B of t equals 6,000 times 1.10 to the t. What was the initial population?
6,000.
6,000. So A was 6,000. So you're just kind of working backwards here. Is it growing or decaying? Growing. How do you know?
Because it's greater than 1.
Yes, because it's greater than 1. And what rate is it growing at? What percentage is it increasing at? 10%. Yeah, it would be 0.1, but we want to convert that into a percent, so it would be 10%. And then it wants to know how long will it take for the population of bacteria to double in number. So you're trying to figure out when it gets to what?
12,000.
12,000. That's the goal you're looking for. So I'm going to stop there.